anywhere in the country? If anywhere, you think Texas would be one where you don't go too close to all the petrochemical plants there are over there. And the other thing here is what we're gonna look at, how it would help to know, if you look at the amount of ammonium nitrate that was stored in that facility and the overpressure that a detonation could result in, that should have triggered something, some other means of storage, right? Either store less or protect it better in the case, because obviously they do have a lot of flammable components in there, toxic chemicals. But the really sad part is the firefighters who had no idea what danger they were in. And they were right, the ones who were killed in the incident, right? Accident, not an incident, that's an accident. Right, and it's incredible that only 15 people died. Did you see the houses that were in the area? Anyway, so hopefully, hopefully this break will make you pay attention in class, so you can help avoid these things. So, what do we have? Well, we have looked at before, if you remember, this is chapter 2 now, but chapter 2 had probative correlations, and some of those correlations was for toxic exposures, but there were also some for damage from explosions, right? There were fire and explosion damage, and we looked at a few, I believe, that you know, how many people would die from lung hemorrhage. You know, what structural damage would we expect, and glass breakage, structural damage, but what we need here, as you can see, is the overpressure, right? So if we can estimate the overpressure that a certain amount of compound would result in if it detonates, then we can at least use these Probit equations, or we can use the table, right, in the book that lists, you know, here is what are sort of the limit for structural damage, for houses, right, and so on. But, so how can we get the overpressure? Well, it depends first on the type of explosion. We can have a chemical explosion, right? That's due to thermal expansion and the increase in the numbers of moles, right, of gas. There's a lot of, for an exothermic reaction, we can have a lot of energy released. Or a mechanical explosion, where you simply overpressurize the vessel. And I'm sure you can realize that a chemical explosion can be much more severe, and that's what we're going to look at, because for a mechanical explosion, right, the result of what the damage is basically due to the energy release, that's due to the pressure difference. Okay, that can be a lot less than what we will be talking about with chemical explosions. Okay. So what we're going to use is a TNT equivalency method. So it turns out that for TNT, which is sort of a standard measure of the strength of a bomb, right? Trinitrotoluene. Okay. They have measured the side-on overpressure at a certain distances from the point of explosion, right, for TNT, so that they have put up some correlations between that distance and the overpressure it generates for a certain mass. Okay, but it's not a straight correlation, so we have to use an equivalent mass of TNT at a scaled distance. So what does it look like? Well, if we plot the scaled overpressure, so that's the overpressure over the ambient pressure at that point on this, to a scale distance that is actually a distance divided by the equivalent mass of TNT, or the mass of TNT in this case, to the power of 1/3. Then we get a curve that looks like this. Okay, so if we know the distance and we know the mass of TNT, for example, that's what this has been developed for, then we can go in here, we can calculate what scale distance that corresponds to, and then read the scaled overpressure and get the overpressure from there, assuming we know the ambient conditions. Okay, so all we need then is to convert the mass of what we have, ammonium nitrate, whatever chemical we have, to an equivalent mass of TNT, okay, which for most cases should be a little bit less than the mass of TNT, right? After all, the TNT is a bomb, right? It's used as a bomb. So scale pressure, scale distance. So what we do to calculate an equivalent mass of TNT is to take the mass of the component we have. Its heat of explosion is really what we need in here, but that may or may not be available. So we would use the heat of combustion over the energy of TNT, and this here is an explosion efficiency. Okay, in other words, you can imagine that all this mass is not going to detonate at once, right? So only part of it will participate in the explosion. So if we look at the numbers, so the energy of TNT, 4686 kilojoules per kilogram, it's given in the book, but it's below the table or below the equation. So that's another one that you would have to know where to find, right? It's listed under, we've had a few equations where you need the mass diffusion coefficient was the other one, right? Where you need to know where to find the information. Usually the explosion efficiency is between 1 and 10%. Okay, so that's not a very high number, but sometimes that doesn't, right? That it's devastating enough, right? And so what you need here, the energy of explosion is usually not available for you, so you use the heat of combustion. And that is given again in Appendix B. Okay, it's given with all the other flammability limits. Okay, so that should be straightforward to use. Okay, so let's look at what we need to do, right, to determine if we have a vapor cloud explosion of methane. We know that it destroyed the house structure 100 feet away from the ignition source. Let's determine how much methane was released and how much, right, exploded. Okay, so we need to calculate, right? We need the scale distance, right? And so we have the distance. So we actually need the scale distance to calculate the equivalent mass of TNT. Only from there can we back out the mass. Okay, so that means we need to find the overpressure, right, that caused destruction of a house structure. Okay, so we would have to go in here. If this wasn't on an exam, I would be very specific on the damage, right, to structure. So there wouldn't be any question. For example, I would say, okay, this explosion caused 50% destruction of brickwork houses, so that you know what I had in mind for you to use. Question? Probably by measuring it, right? You know you have this much, right? You know that this would be equivalent to a certain amount of TNT. And then if you ignite it, you only get 1 to 10%. And a lot of the equations that we have used, they're empirical equations, right? It's at least better than nothing. Because I think that if someone had taken a look at West Fertilizer and look at the amount of ammonium nitrate they had stored, and they had even looked at this equation to try to determine what kind of overpressure we could have if this exploded, or if a fraction of this exploded, then they probably would think twice before they allow anyone to build nearby. okay? Because we know, we have seen, it's the pressure wave, right, that destroys houses. They.
I guess a follow-up, would that be
Mhm.
true only from the explosion, or would as a follow-up, would that be
Yeah.
different only from the chemicals used in the explosion, or would it also be affected by like the exposure efficiency?
You know, so did everyone hear that? Right, the explosion efficiency will be dependent on the chemical, right? It will be dependent on other things. So it's a rough estimate. So, I mean, if you, to play it safe here, I would, right, pick an explosion efficiency of 10% because that would give the largest damage, right? You could pick 5 to have an average, but it depends on a lot of things. There are very good questions. Yes? The worst possible would be 100%, but it's unlikely that all of it participate in the, so that's the bottom line here. If you have 30 tons of ammonium nitrate, for example, what this equation tells us that it's unlikely that 100% of that will participate in the detonation, right? It's more likely that 1 to 10% participates. But if you store that much, right, it's the destruction distance is what's going to be influenced.
You mentioned a lot of these things are very empirical. How do we go about measuring these things safely?
That's another good question. How do you measure this safely? Because obviously the empirical equations, right, that has been measured has been done on small amounts.
With
There's
Legos?
obviously no one that's going to go and set off, unless you're the Department of Defense and you're out in the middle of nowhere, then you can set off a bomb, atomic bomb. No. Take that.
Rough estimates from, say you don't know what your delta-H combustion is, but you know the delta-H combustion of two other materials that like have to do a reaction.
If you're similar, right. So now delta H of combustion and things like that, those are numbers that if you don't find them tabulated, you know how to do, right? Because you can go and find enthalpies for almost anything, right? And you can calculate a delta H from reference states. So even if you don't have that specific number, you can go and find there are enthalpies for reference state, reference compounds. So you can get that. It's been a while since you did that, but I'm sure if you start looking at those numbers, that's chemistry something, right? So it's not a matter of those heat of combustions are available, and it's particularly for a lot of flammable hydrocarbons. You're gonna have more data than you want probably on that. But this equation in particular here, where they have measured the side-on destruction from TNT, obviously that they have blown up TNT various amounts. The question is, how far did they go? Did they go to ton scales or not?
Right. So that's what I was wondering is how did they get these things like
On this scale.
Is it all just
Well, you know, the Department of Defense are pretty good at bombs, so I am sure that a lot of this has been, and they have a lot of money. So I think that I wouldn't be surprised if this is rather accurate. Right? I could be wrong about that. I wouldn't. This is not right. I am not, and I prefer not to work with explosives. If you remember that, it doesn't take much. Well, what were they doing? They were in Texas Tech. The grad student was working on it wasn't ammonia. It was some kind of perchlorate, and they were supposed to keep it at milligram scale, and they scaled up to 10 grams. And this is 10 grams now, but that was enough to fracture the bench and blow the student's arm off. Okay, so for of course at that level you can get pretty accurate readings because you can detonate that in a safe environment, right? If you really wanted to. But when it comes to this equation, I wouldn't be surprised if there are a lot of data available for this. It is just not necessarily available to us in other form than this, right? Okay, oops. So where the wording, so where let's not get sidetracked here now. We were trying to find how much methane exploded if we destroyed a house structure 100 feet away from the ignition source. Okay, so what are we looking, what overpressure are we looking at? Right, so this is where you would find that. Like I said, on an exam I would be very specific, so there wouldn't be a question on what I want you to use, what number. Probably the one that's the closest is here, 5 to 7 PSI gauge, nearly complete destruction of houses. Okay. So for that, if we're trying to find the smallest possible, right, the smallest weight, I would use 5 instead of 7, right? We don't really know. So we have our P0 would be roughly, I would say, 5 PSI gauge. Because 5 to 7 PSI gauge result in near destruction. What do we say? Near complete destruction of houses. Okay, so from that, what we needed was scaled pressure, which is P0 over P ambient. So if we use 5 PSI gauge, okay, this is not P0. Don't get that confused, right? Because they use P0 in all the leaking gases, right? From things. This is supposed to be an O, is in my opinion, because it's P over pressure, which means we need to gauge pressure, right? And hopefully if you make that mistake, you will soon realize it when you try to look at the graph. Okay, P over pressure, 5 PSI gauge, that should be in gauge pressure, absolute. That is equal to 0.34. If we use 6, right, since we don't really know near complete destruction and destroyed a house, 6 PSI gauge, for example, will give us a PS of 0.4. And if we look at this graph here, 0.04, 0.034, since it's a log graph, right? I'm not sure that I can put 0.34 accurately on there, so I picked 0.4, right? So 0.4 is our PS scale of pressure. 0.4 we go out here, and then again it's log. So when you do that, remember that this is 1, so this would be 2, 3, 4, 5, and 6. Okay, so this is figure 623, we get that the scaled distance is equal to 6, and that was equal to R over the equivalent mass of TNT to 1/3. Okay, R in this case was 100 feet, or 30.48 meters, right? That it's important to note the units. It's meters